Hello, and welcome back to EECS 367, Introduction to Autonomous Robotics, and Robotics 320, Robot Operating Systems. This is now our 12th lecture of the winter 2022 semester at the University of Michigan for the AutoRob course. The topic for today's lecture is going to be inverse kinematics, where we'll be focusing on optimization-based solutions to the task of inverse kinematics. So you'll recall that from last week's lecture that we began talking about inverse kinematics with closed-form solutions, where we were trying to find the joint configuration of our robot in order to satisfy our desired end effector position. And so today what we're going to be looking at are a variant of those techniques that are going to be based on optimization instead of closed-form approaches. But before we get started, I'm going to go ahead and minimize myself so that we can all see these slides. So the first thing that I want to mention today is once again just a reminder about the new robot definition feature that was part of assignment 3. So as just a reminder, so everybody's going to work in pairs for this new robot definition, where you'll describe a new robot in our URDF JavaScript format. And coming up this Wednesday, February 23rd, each team is going to showcase their robot to the class during our interactive session. And so everybody will have 1 to 2 minutes to come up and display their new robot description to the class. We'll have pizza available, and I'm really looking forward to seeing what everybody has come up with for their new robot description. And in terms of the point breakdown, so there will be 1 point for this feature as long as your new robot description is compatible with our forward kinematics routines. And then the second point will be for showcasing your robot during the interactive session on Wednesday. So I just wanted to mention this one more time just to make sure everybody remembers about this Wednesday's interactive session. So with that, so let's go back to talking about robot kinematics. So we've looked now at forward kinematics from lectures 7 through 8 and with our assignment 3, where we were trying to infer the pose of the end effector given the state of each joint. And last lecture, we started talking about inverse kinematics, where we were trying to infer the joint states that would be needed for our robot arm to be able to reach some desired end effector pose. And in particular, last lecture, we looked at closed-form solutions to inverse kinematics, where we would use the known geometric properties of the robot itself in order to derive these the needed joint states in a set of closed-form equations. And so within our robot operating system, these both forward kinematics and inverse kinematics fit in to the kind of core modules that we would need for our robot operating system to be effective with a broad array of robots. And so as a refresher about where we stand within the course layout and what projects we have worked on and where we're going. So this slide, once again, is sort of illustrating the kind of core functionalities that you might want within a robot operating system and where they fit within our course. And so in particular, so currently this lecture and our last lecture are focusing on inverse kinematics, where coming up then we'll be looking at motion planning, decision making, and collision detection. So for inverse kinematics, there's sort of these two possible approaches, right? So in the last lecture, we talked about closed-form solutions, where the known geometry of the robot can be used to infer satisfying conditions for the inverse kinematics problems, where we saw that the benefit of these closed-form solutions was that the computations would be very efficient, often in constant time, and in addition, these closed-form solutions would be very predictable, where you could typically guarantee that they would be able to perform based on the geometry of the robot. The downside that we saw with closed-form solutions was that they would be sort of brittle and only work with a specific robot structure. And so to solve that problem, there's a separate set of approaches within inverse kinematics that use optimization in order to actually find those desired joint states. And so the way that, at a high level, that these optimization techniques work is they'll try to minimize some notion of error between the current end effector's position and the desired pose of the end effector. And so that's what the topic of today's lecture is going to focus on, are these optimization-based approaches to inverse kinematics. And so oftentimes these optimization approaches are going to be solved by some form of gradient descent, where the benefit of this approach is that we can generalize our solution to inverse kinematics for a broad array of robot geometries, so that our implementation is not only applicable to a single robot structure. It can be applied across different kinematic structures. And so one thing that we mentioned during last lecture that is kind of a really nice illustration of this idea of inverse kinematics was this web demo, which is linked here, that was illustrating how a three-link robot could sort of be applied within this inverse kinematic setting, where you would try and reach the end effector on this three-link robot to reach the desired poses. And it was set up as a game. So I'm curious, I'll make a post on Slack where we can all share what our best score was. I can only tend to get around 12 of the set points in a minute when I'm manually controlling the robot. And so that illustrates that the inverse kinematics problem can become quite challenging when you have these multiple degrees of freedom embedded within the robot. And so one thing, right, that we want our robots to do is for them to be able to operate autonomously, where they can solve this inverse kinematics problem on their own. And so that's what we're going to focus on today. And so if you're curious, so Professor Jenkins has implemented an extension to this particular demo, which you can view by following this second link, where he actually implemented for inverse kinematics within this three-link arm framework. And so this inverse kinematics implementation is going to be similar to the one that we're going to be talking about today, and also the one that we'll be working on for the upcoming assignment 5. And so in particular, if you follow this link, what you'll find is that this demo here will show what Professor Jenkins implemented, where no longer is the robot being controlled manually. Instead, we have the combination of inverse kinematics and a PID controller to actually execute the desired joint angles to reach each of these set points. And so this robot is much, much better at finding the desired set points than I am, and in fact than most people are. If I'm remembering, I think the world record on the manual control example was something in the 20s, like upper 20s, whereas this robot, when it's made automatic with inverse kinematics, can get in the 80s in the 80s of set points per minute. And so it's really quite impressive. One thing you're noticing, right, is that, as mentioned on the slide here, this particular controller that was implemented is fairly aggressive, where it has a lot of that kind of very back and forth motion, and so that's not that's just a result of the particular tuning of the PID control component. So we can still apply inverse kinematics with a more conservative tuning to have very smooth natural motion, which is shown on this modified controller here, where, as is familiar to us from our pendulum example, one of the sacrifices to having some of this smooth motion is that you don't reach quite as many set points in the same speed, but you have much more kind of natural, safe trajectories that the robot ultimately will follow as it tries to reach the set points. So how is this possible, right? So how are we actually having the robot automatically sort of configure its joints and its joint states in such a way that it can reach these desired end effectors? So the answer to this question is by using a method within inverse kinematics known as the Jacobian transpose. And so this is the first approach to inverse kinematics that we'll be looking at today, and it's the one that was implemented in those examples by Professor Jenkins on the past couple of slides. So let's look at how we can model this system within the framework of inverse kinematics. So the high-level goal of inverse kinematics is going to be to move the end effector's position to some desired target location. So in this demo, the end effector's current position is shown at the tip of the third link on the kinematic chain. So it's at the very end of this orange link where my cursor is. And the desired location for our end effector is shown by the blue set point over towards sort of the left-hand side of the workspace. And so the goal then that we can sort of imagine is we want to move this end effector from its current position to the desired position. And so at any given instant, if the end effector has not yet reached the desired target location, then we can think of there being some error with respect to this desired location. So in other words, this difference between the end effector's current position and desired location can be thought of as an error that we want to minimize. And so the goal then of inverse kinematics, and the question that inverse kinematics poses, is could we move the end effector's position in order to minimize the error? And in particular, how should we move the end effector's position in order to minimize this end effector error? And so one way that we could reason about doing this is by trying to relate the end effector's linear position with the angles of rotation that each of the degrees of freedom within the pendulum take. So if we think about the end effector error, this displacement error, as being a sort of linear velocity that we would like for the end effector to take, then if we could convert that linear velocity at the end effector into the corresponding angular velocities at the joints, we could then reason about how the end effector can be moved in this desired direction that will minimize the error in our end effector's position. And so we'll treat this error as a displacement in position, which we can think of as being a sort of desired linear velocity that our end effector should take to minimize the error. And we then want to be able to reason about what joint displacements, which can be thought of as angular velocities, will correspond to this desired end effector displacement. And so this is what we want to do. We want to be able to relate these two types of velocities: the linear velocity of the end effector in terms of its position, and the angular velocities of our joints in terms of their rotation at each of the degrees of freedom. So how should we think about this relationship between the linear and angular velocities? Well, one way that we can start thinking about it is by first considering the velocity and the motion of a single point as it rotates within space. So a good demonstration of this is actually a single pendulum, which is demonstrated here by this yo-yo that's swinging around a rotational axis that you can think of as kind of extending out of the screen straight from in the direction of Professor Jenkins's thumb there. So if we look at this illustration, let's kind of notate down all the pieces of it so that we can relate it back to our robotic arm. So in this case, we're going to be considering the motion of this point. That's the position of the sort of bob of this pendulum at an instant in time. So if we think about this point here, so it's first of all, it's rotating about this axis. So we have the axis of rotation, as I was saying, can be thought of as extending out of the screen that you're watching this video on, sort of out of the plane. And about this axis, the point has an angular velocity denoted by theta dot. So the angular velocity denotes how fast the point is rotating about this axis of rotation. In addition, the point itself is translated this distance away from the axis of rotation, which is this blue vector. And at that location in space, at this instant in time, there's a linear velocity denoted by this green vector, which is tangential to the circle representing the point's motion in space as it rotates. So given this, right, so our goal was to be able to relate the angular velocity of the point with respect to the linear velocity of the point. And so it turns out that we can relate these two values in the following way. So the first thing is we denote the angular velocity of the point in this equation here. So we take the rotational speed given in like sort of radians per unit time, and we multiply that by the rotational axis, which again will be some axis in 3D space, and that gives us our angular velocity. And at that point, we can then derive the linear velocity with the following equation. So we can say that the linear velocity is equal to the angular velocity cross product with the with the position of the point relative to that axis of rotation. And so if we substitute in our term for angular velocity, we have this final equation. So we have our end effector velocity as a linear velocity is equal to the rotational speed multiplied by the rotation axis, and then cross product with the position of the point relative to the axis of rotation. And so within our robotic example here, what that would look like is if we focus just on the first rotational degree of freedom here, if it has some angular velocity theta dot, that's going to induce a linear velocity shown by this vector v. So we've now arrived at the point where we can relate a linear velocity with a given angular velocity, right? Which is which is sort of in the direction that we were trying to go towards, but this is not exactly what it was that we were looking for when we set up our inverse kinematics problem in this three-link arm robot. And so why is that? Well, it's because this relationship that we've described here doesn't specify how it is we can obtain a desired joint angular velocity from a given linear velocity, or that linear displacement vector that we were looking at, right? So in other words, what we really want is we want to say, well, we know what the linear displacement is, what angular velocity will kind of align with that displacement. Instead, what this equation says is if we have some known angular velocity, we can calculate what the induced displacement is, which is not going to necessarily be the displacement that we're desiring for our inverse kinematics kind of setup. And so how is it that we can obtain the desired joint angular velocity? Well, it turns out that we can use the Jacobian transpose method. And so what's shown here in this final equation is the Jacobian transpose sort of method applied in this case of a single rotational joint here, which is represented by the delta theta, which will be induced by a desired displacement delta x and this transpose Jacobian. So if we look at the terms within this equation, so the first thing we're going to have is, so the result of applying this equation is going to be an angular displacement that our joint should take in order for the end effector to move along this desired displacement vector delta x. So here we have our desired displacement vector for the end effector, and the middle term then is what is the Jacobian transpose. So this superscript t denotes transpose, and this inner term here is what's referred to as the Jacobian for this joint. And so the Jacobian transpose method is a way of approximating, inducing a linear displacement that aligns with the ideal displacement vector that we're after. So it's a way of approximating that ideal displacement vector, and it tells us exactly what angular displacement we should cause to move in that direction. And so the procedure for this Jacobian transpose method is then described here. So the first thing that we would do is we can compute the Jacobian based on the current state of the system. We can update the joint angles using the Jacobian transpose, which essentially will result in motor commands going to the actual angles to induce torque to cause the displacement. And then we would repeat until convergence. So the second step will cause some new state of the system. So then we can go back, compute the new Jacobian for the new state of the system, and repeat this process over and over again until the system converges on the desired set point for our end effector. And so it's an iterative approach. And like I was saying, it turns out, and we'll talk about this more later on in the lecture, that this Jacobian transpose approach, it's a way of approximately minimizing that error between the current and the desired end effector location. So it's an error minimization technique. So let's take a closer look at how it is that error minimization relates to our inverse kinematics framework. So typically when we're talking about error minimization, one of the most common approaches that comes up is this technique known as gradient descent, which we'll be looking at. But before we look at gradient descent, let's set up our problem here within this error minimization context. So the first thing we have to do if we want to minimize an error is we have to define some notion of error that should be minimized. And so the example that we've been looking at with this 3-link robotic arm has used the definition of error as being the difference between the current end effector position and the desired end effector position. And so this error then is parameterized by the current robot configuration, which on the slides here is denoted by the variable Q. And so the goal then of error minimization is going to be to find the configuration Q that minimizes this error function E. So that can be expressed mathematically with this argmin function, which is shown here, which is just saying that we're going to find the configuration Q, which will globally minimize this error function E. And so this, expressing error minimization in this way then motivates the question of how it is we can find this argmin, and in particular, how can we find this argmin if we know what the equation for the error was in closed form. And so it turns out that from using our knowledge of calculus, we actually do know how to find the global minimum for closed form for certain types of closed form functions. So one example that we can look at is on this slide, where we have given to us this quadratic equation, right? So it's a function that takes this specified form here, shown with f of x. And so we know from calculus that we can find the global minimum for this function if we first take the derivative of the function with respect to x, and then we solve for the variable x where the derivative is 0. And we know that will be the global minimum value. So if you want to work through this process as an example, you can pause the video here and work through it. But I'll step through it now as well. So the first step is to take the derivative of this function. So using the chain rule from calculus, we can solve for the derivative shown here. So this df dx is going to be 6 multiplied by x minus 2 multiplied by 1. So we have the first component here is the derivative of this sort of outer portion of this function, and then this standalone 1 is then the derivative of the inner portion with respect to the variable x. So that's applying the chain rule. And so if we solve for this, for this variable x by assigning the derivative value equal to 0, we'll find that when x is equal to 2, the derivative of the function is equal to 0. And so you could then plug this value into the function and evaluate it to find the minimum value for this function. But in addition, we can then plot this process. So shown on this slide is that same function plotted with the blue curve. So we can see the quadratic curve is plotted in blue, and then the derivative of the function is plotted as the red line. And so we can verify that at the point at which the derivative crosses the x-axis, so at the point at which the derivative is equal to 0, does correspond to the global minimum for this function. And so for this particular function, it turned out that there was a unique solution to the case where the derivative of the function was equal to 0. But not all functions have that same property. So in particular, the function plotted on this slide, we can see has not only a global minimum, but in addition, it has local extrema. So there are local maximum and local minimum where the derivative of the function would still be equal to 0. So for example, here's a local maximum that will have a derivative equal to 0, which you can sort of visually observe by imagining what the slope of the function is at that point. It would be indicating a slope of 0. And similarly, this function has a local minimum at this point, which is different from the global minimum, but would still share that property of having the derivative at that point being equal to 0. And so we could also check this. So for example, we could calculate what the derivative of this function is with respect to the variable x, and then we could plot the resulting derivative function along with the original function. So the derivative in this case, once again, is plotted with the red line, and then the original function is plotted with the blue line. And the thing that we can denote is that every single point at which the derivative of this function crosses over the x-axis at the 0 point will correspond to a local extrema of the function. So if we zoom in, for example, we'll see that there are many points at which the derivative of the function is equal to 0. And so if we wanted to calculate what the global minimum is for this function, we would have to compare the value of the function at each one of these crossover points using the technique that we've described. And so that would require a number of comparisons to find the global minimum. So if we would want to apply this technique to our case of inverse kinematics using error minimization within this robotic end effector problem, we would need to know a closed form expression for the error, and we would also need to know how to take the derivative of that expression with respect to the configuration, and then we would need to do a number of those comparisons potentially in order to find the global minimum where the derivative of that error function was equal to 0. And so this can be challenging to implement in practice for a number of reasons. First of all, if we don't know the closed form expression for the error, or if we're not able to take the derivative, or if the derivative would require many comparisons in order to find a global optimal. And so for this reason, this approach might be difficult to implement in practice. And so in contrast, what we will typically do is instead of trying to find a global minimum for the error, we'll instead resort to finding a local minimum using an approach that we will be certain can be implemented, which is known as gradient descent. And so this slide here is highlighting at a high level gradient descent, which is working up towards our Jacobian transpose that we looked at the beginning. And so within gradient descent, we define some function, and we're going to iteratively take steps by changing the input to the function in order to try and minimize the function's value. So in our case, the function that we're interested in minimizing is our error function, which is defined with respect to configurations. So in this diagram, we can think of this function f of x as being our error function, and the variable x, so the input to our error function, as being the configurations of our robot. And so our goal then is to find the configuration, which is going to be somewhere along the x-axis, that minimizes the error function, right? And so the high-level idea behind gradient descent is we're going to make some initial guess at what the robot configuration would be. So we'll call that guess x0, and then we're going to repeatedly take steps. We're going to repeatedly modify our initial guess in the direction that is minimizing the error, or that is at least decreasing the error value. And so the second line here, this equation is representing that idea expressed mathematically. So the idea is we're going to update x, so we're going to have this new x at I plus 1 based on the current kind of guess of a solution, which is x sub I, which is being modified by taking this step along the gradient of our error function, which is expressed here, the gradient of our error function at the point of our current kind of best guess. And we're going to repeatedly take these steps until we converge, so until our step size becomes small. And so let's look at what that looks like graphically. So the first thing we're going to do is we're going to make some initial guess. So let's say we pick some initial robot configuration shown here, and we evaluate its error, right? So our initial guess for the robot configuration is going to have some error that's non-zero, and we're going to try and minimize it. So the first thing we're going to do is we're going to evaluate what is the gradient of our error function at this point, which we can visually think of as being the slope of the line, which is tangent to the curve at this point x that we've chosen, our x is 0. And so if we take then a step so in this case, the slope is in the negative direction, right? So it's going to be pointing downward. And so if we take a step in the negative of that direction, which is what's expressed here, so we have the negative of this gradient, is going to move our second guess in the positive direction. So our next guess then is going to, so like I was saying, the rate of change of this gradient is going to be negative. So our next step is going to be in the positive direction. So we might have some next step here. At that point, we'll have a new error, which again, we can now repeat our gradient descent. So we're going to evaluate the gradient at this new point x sub
let's say x sub 1, it's going to, again, the gradient is going to be negative, so we're going to take the next step in the positive direction, and we're going to repeatedly take these steps until we've converged, until we've reached this local minimum of the function where our steps are no longer moving us in the horizontal direction. And so at that point, we'll have reached a local minimum where the derivative of the function would be 0. And at that point, our gradient descent would have kind of completed. And so this technique is very promising, and it's typically very easy to implement in practice. But to do it, what we have to, the one constraint we have to be able to do first is we have to define what is the derivative of our robot configuration. Or maybe said a little bit more explicitly, what we're really interested in is being able to define what is the rate of change of our end effectors pose with respect to the current robot configuration. And so this idea, this value, is what's known as the geometric Jacobian for our robot. So you'll recall from earlier in the lecture, we actually saw an example of the geometric Jacobian when we looked at the Jacobian transpose applied to 1 degree of freedom on our 3-link robotics arm structure. And so what we want to do now is we want to extend the idea of a geometric Jacobian to handle all the degrees of freedom that exist within our robot beyond just a single rotational joint. And so to do that extension, the Jacobian itself is going to extend from being a vector, which is what it was in that earlier example, to now being a matrix. And in particular, the Jacobian for our purposes is always going to be a 6 by n matrix, where the n column vectors within the Jacobian correspond to each of the degrees of freedom that can affect the end effector's position within the robot. And so each column within this matrix we can think of as representing a transform that will transform the velocity at the end effector to a velocity at the corresponding degree of freedom, and where each element within the matrix represents a partial derivative. And in particular, based on that element's position within the overall Jacobian matrix, it will represent a specific partial derivative between one element of the result of forward kinematics run on the robots to produce the end effector's state, and one of the degrees of freedom within the robot. So we'll look more at this in detail. The first thing I want to mention is a couple of notes on this figure. So this figure is taken from Spong, and it's illustrating an example of a kinematic chain robot, where we have a base link, which is the base frame of the robot here at index 0, and then we have our end effector at index n. And then within the robot itself, you can see we have these additional degrees of freedom. For example, this rotational degree of freedom, a prismatic degree of freedom here. And so collectively, then this makes up just an example kinematic structure, which we can think about as, in this case, representing an n-link arm in three-dimensional space. And so what you'll recall from forward kinematics, right, is that we will be able to produce a transformation from the end effector frame to the base frame, to the world frame, which will be based on the current configuration of the robot. And that transformation will be represented as a homogeneous matrix. So this is what we looked at you'll recall from assignment 3. So to go back to the Jacobian, so as I mentioned, each element within this Jacobian matrix is going to represent a partial derivative. And so the Jacobian is going to take the form that's shown here on the lower right-hand side of the slide. So based on the position of each element within this matrix, the value that exists within the matrix then is going to represent one particular partial derivative that is going to relate the output of our forward kinematics. So one of the variables that output from our forward kinematics, representing a portion of the state of the end effector, with respect to one of the degrees of freedom. So the the variable f in this matrix represents the output from our forward kinematics, and each variable x then represents one of the degrees of freedom along the robotic structure, where the index of the x denotes which joint the degree of freedom corresponds to. So x1, for example, would represent the first joint, the degrees of freedom that correspond to the first joint, whereas x sub n would represent the nth degree of freedom along the chain. And then similarly, the subscripts of the f variable correspond to, like I said, the different elements that are output from our forward kinematics. And so in the case of an end effector, that's going to be three components representing the position of the end effector in XYZ space, or it's a 3D space, and then an additional three components representing the orientation of our end effector. So what we can do is we can think about this Jacobian as being broken into sort of two 3x(n) matrices, where the upper 3x(n) matrix represents the Jacobian specifically with respect to the sort of velocity of the end effector, meaning we're considering only the partial derivatives of the position of the end effector with respect to all n angles. And then the lower 3x(n) matrix within this Jacobian represents the orientation components. So it's representing the partial derivatives of the orientation of the end effector with respect to each of the degrees of freedom. So just once again, just to reiterate, is that one element within this Jacobian represents we can think about it as representing the change in an end effector variable with respect to a change in one of the joint variables. And so this is going to be very useful for us as we try and solve the inverse kinematic sort of problem using gradient descent. So moving in that direction, the first thing that we can observe about the Jacobian is that it relates the velocity of our end effector to the velocity of our joint configuration. So in particular, what we can do with the Jacobian is if we multiply, let's say, the 3x(n) velocity component of our Jacobian by a vector representing the joint angle velocities, we can actually produce the linear velocity of our end effector. And similarly, if we take the 3x(n) angular component of our Jacobian and multiply it by that vector of joint angle velocities, we can produce the angular velocity of our end effector. And so this is moving us somewhat in the direction of inverse kinematics, but of course what we want to be able to do is sort of the inverse of this operation, right? So what we're interested in is deriving the joint angle velocities that would be needed in order to satisfy a particular desired end effector orientation, and the joint angle velocities needed to satisfy a particular end effector position. But before we can get there, let's next look at how it is we can actually construct the Jacobian given the current configuration of our robot. So in particular, the forms here shown on this slide carry over for any of the robots that we'll be considering in this course. So robots that are a combination of prismatic joints and rotational joints can have their Jacobian defined in the following form, where for a particular prismatic joint, let's say J sub I, being some prismatic joint, we'll have a corresponding column within the overall Jacobian defined as the first three components being the axis of translation for that particular prismatic joint, and then the lower three elements within that column being all zeros. Similarly, for a rotational joint, the corresponding column within the Jacobian is defined on the right-hand side of this slide here. So the first three components of this vector represent the axis of rotation for this joint, cross product with the vector that points from the origin of the joint to the origin of the end effector, and the lower three components of this particular vector correspond to just the axis of rotation for this rotational joint. And so using these two formulas here, we could then construct the Jacobian matrix for our robot given its current configuration. And from that, then we would be able to have a resulting 6x(n) matrix for our system. And so one thing I want to point out is some of the notation here in relation to our figure. So to highlight, so first of all, so within this figure, so O sub n denotes the current position of the end effector with respect to the base frame, which we can think about in this case as being the world frame. So this O sub n is a vector, so it's a 3D vector that points from the origin of the world, in this case the origin of the base frame, to the end effector's position. O sub I minus 1 is also a vector that points from the base frame to the origin of the joint corresponding to joint I. So this O sub n minus O sub I minus 1 then is also going to be a vector that is with respect to the world frame. But before we get there, the other notation I want to point out is that this z sub I minus 1 will correspond to the axis of either rotation for a rotational joint, or in the case of a prismatic joint, it'll be the axis of translation for this particular ith joint. So this z sub I minus 1 for this joint here will correspond to this axis of rotation within our figure. So from these definitions, we can observe a few things. So the first thing that we can observe is if we look at this vector here, so O sub n minus O sub I minus 1 is going to be a resulting vector, which in this figure is illustrated by the blue by this blue vector shown here. So it's going to be a vector that points from the origin of the current joint to the position of the end effector with respect to the world frame. In addition, then the cross product with that vector and the joint axis is going to then be another vector in the world coordinate frame, which we can think of as lying along the direction that rotating this particular joint would move the end effector in the direction of. And so what this resulting column vector then can be thought of as representing is the relationship between a change in the joint angle for this rotational joint with respect to a change in the translation of the end effector. Another important thing to point out about this Jacobian that we've discussed so far is that all of these quantities have to be expressed in the world coordinate frame for the definitions to hold. And so in addition to that, on this slide, what we're showing here are a couple of useful relationships that will help kind of define what each of these axes and vectors are. So the first thing, right? So the end effector is going to be expressed in the world coordinate frame. So if you transform the position of the tool into the world coordinate frame, that denotes the O sub n on the previous slide. So it's the vector in the world coordinate frame denoting the position of the end effector. Similarly, this O sub I is going to be in the world coordinate frame, representing the origin of the particular joint, which has been transformed from its local origin into the world coordinate frame. And then the joint axis, right, so the axis of rotation for our case, is going to be also transformed from the local frame of reference of the particular joint into the world coordinate frame according to the forward kinematics transform that we calculate. So this shown in the red box here is just a restated version of our column vector for a rotational joint within our Jacobian matrix that is simply re-expressed in terms of these transformed variables here, just to help with kind of connecting this description of the Jacobian to our forward kinematics implementation of the transformations from local frame to world coordinate frame. So let's look at how this geometric Jacobian was derived. So if we start with angular velocity, it turns out that the composed angular velocity for the end effector can be expressed as a composition shown here, where we take the angular velocity at each of the joints, transform each of them into the world coordinate frame, and then sum in order to arrive at our resultant angular velocity for the end effector. So as a result of this, if we take the partial derivative of the angular velocity with respect to one particular degree of freedom, so one of the particular joint angles, what you'll find is that it ends up being that particular axis of rotation rotated about the corresponding rotation transformation of that specific joint. And so this is how we derived the values that were used within our particular column vector, making up the angular portion of the Jacobian. To calculate the corresponding linear components of our Jacobian, we followed a similar process. So if we first basically take our transformation from the end effector frame to the world coordinate frame based on our configuration, we can derive the composed homogeneous transformation matrix, which is shown here and should be familiar from our discussion of forward kinematics, right? And so based on this, then we can pull out just the positional component of this transformation, which denotes the position of the end effector with respect to the world coordinate frame. And at that point, to find the corresponding Jacobian, what you do is you take the partial derivative of this position with respect to one particular joint angle. So taking the derivative of this with respect to the ith joint angle will end up resulting in the cross product form that we found for our linear velocity component of the Jacobian. Now that we're familiar with the geometric Jacobian and the properties of the Jacobian, let's go back and let's restate the inverse kinematic procedure with this new understanding of the Jacobian matrix. So just as a refresher, right? So we've got this 6x(n) Jacobian where each column corresponds to one of the degrees of freedom and represents this relationship between an angular velocity of our joint configuration and the corresponding velocity either in the linear term or the angular term for our end effector. So based on this Jacobian, what we can do for inverse kinematics is what's illustrated on the lower left-hand side of the slide here. So the first thing is we can compute the end effector error, so this displacement based on our desired pose of the end effector and our current pose of the end effector. We can then, using the inverse of our Jacobian, we can calculate a direction in configuration space that we want our robot to take, so this delta Q, to be equal to the inverse of the Jacobian multiplied by this displacement in the end effector pose. And based on that delta in the configuration space, we then know how to update our current configuration by taking a step in the direction of this delta Q sub n. And so we can iteratively do this procedure, right? So we can iteratively take these steps in configuration space, and our Jacobian is going to ensure that these steps are going to be moving our end effector in the direction of our desired pose. But this presents the question, right? Is that if this setup for inverse kinematics will lead to our end effector being in our desired pose, it's predicated on our being able to invert this Jacobian matrix. So then the question, of course, is, well, when can we invert this matrix? So one thing, it's worth thinking about this for a little bit, maybe. So maybe you can pause and think about when it is that we can invert this matrix. But it turns out, right, so for one thing, we can only invert square matrices. So this 6x(n) matrix would only be square in the case that we have n degrees of freedom being equal to 6. And even within that case, even when it is a square Jacobian matrix, there's still not necessarily a guarantee that the matrix itself will be invertible, even if it is square. So this motivates kind of re-looking at how it is we're sort of thinking about inverse kinematics and if there's alternatives that we can use to ensure that we can always perform at least some procedure to move our end effector towards the desired pose, since this inverse Jacobian isn't always going to be available to us. So this brings us back to the Jacobian transpose that we looked at the start of this discussion on inverse kinematics using optimization. And so in particular, what the Jacobian transpose is going to propose doing is it's going to propose defining this step in configuration space to be equal to the Jacobian transpose of based on our current configuration multiplied by a step in or a displacement in the end effector pose as opposed to the Jacobian inverse. And so the principle behind this is that we're projecting this difference vector delta x onto the dimensions within the configuration space that can reduce this displacement vector in the pose of the end effector. And so the advantage of this over taking the Jacobian inverse is that we can always take the Jacobian transpose. So there is no, and it's a very simple computation to take the Jacobian transpose. You simply have to calculate the Jacobian matrix, which can be done typically in constant time. And at that point, then we don't have to take an inverse. The downside with this approach is that it typically requires many iterations until convergence. And in addition to that, it's not going to result in predictable joint configurations. And the principle behind how it is that this Jacobian transpose works is based on least squares minimization. And so it can be shown that taking the Jacobian transpose and using the Jacobian transpose to form these steps in configuration space corresponds to gradient descent. So it corresponds to minimizing the cost function, which is defined on the upper portion of this slide. And so that's sort of the principle behind how it is that the Jacobian transpose really is working. It ensures that each step that we move will correspond to some degree of minimization of the cost function, where the cost function measures this difference between the target pose of our end effector and the current pose of our end effector. And so contrasting the Jacobian transpose with the Jacobian inverse approach, so to recall, right, so what the Jacobian inverse will do is it'll give us a mapping from end effector displacement to configuration displacement here. But the inverse of the Jacobian is rarely an option, right, typically because the number of degrees of freedom on our robot will be larger than 6, right, so it won't be a square matrix, so it won't be invertible, the Jacobian that is. And so instead, right, so what the Jacobian transpose is proposing to do is to find a configuration displacement that will minimize the end effector error squared. So we're going to be doing this optimization over this argmin here. And so to derive how it is that this minimization actually occurs, so what we're doing here is we're defining this cost function expressed as the error squared in the end effector position. And so if you derive what that cost function is shown here in terms of the Jacobian, what you can then do is we can then try and find what value of the configuration displacement minimizes this cost function. So if we take the derivative with respect to the changing configuration, and we then evaluate this derivative at the convergence point where the change in configuration is 0, what we'll ultimately show is that corresponds to taking a step along this Jacobian transpose multiplied by the displacement in end effector position. And so this is how you can derive that the Jacobian transpose does in fact minimize this error when the error is defined as the squared error between the end effector pose, the squared error in the end effector pose. So looking at an example of what type of behavior this approach will produce. So an example implementation of this Jacobian transpose method is shown on this slide, where there was a multi-link robot that was attempting to solve the inverse kinematics problem to move it towards this desired end effector position here. And so you can see that the resulting trajectory of the points taken taken here. And so this does sort of highlight that you can see like it took, towards the end in particular, it took quite a large number of iterations to ultimately reach the desired end effector pose, which is quite typical of the Jacobian transpose method. It does tend to take a large number of iterations to reach the local minimum there in the cost. So the Jacobian transpose is one approach that we can take to defining this change in configuration, but it's not the only one. So another approach to handle that inability of inverting the Jacobian is what's known as the Jacobian pseudo-inverse approach. And so the Jacobian pseudo-inverse approach is shown on this slide. So we define a step in our configuration space based on this pseudo-inverse of the Jacobian matrix multiplied by our displacement in the end effector position. And so the principle behind the Jacobian the pseudo-inverse approach is to find the shortest path in configuration space, where the advantage of this is that it's computationally fast, but the downside is that we have to take at least one matrix inverse, and so that can lead to numerical instability issues. And in addition, just like the Jacobian transpose, we can result in unpredictable joint configurations. So an illustration of the Jacobian pseudo-inverse is shown on this slide. So you can see that there is a distinct trajectory compared to the Jacobian transpose. So the first example we looked at, the Jacobian transpose, is shown on the left-hand side of this figure versus the same setup but being implemented and solved by the Jacobian pseudo-inverse as shown on the right-hand side. To further contrast the pseudo-inverse method with the Jacobian transpose, the derivation for the principle behind the pseudo-inverse method is shown on this slide, which is similar but distinct in a subtle way. So first, we define the cost function just as we did for the Jacobian transpose derivation. So the cost function is going to be the squared error in the pose of the end effector. We then take the derivative of this cost function with respect to the change in joint configuration, but instead of evaluating this derivative at the where the changing configuration is zero, so where the changing configuration is sort of stabilized, instead we take the approach that we looked at from the sort of first half of this lecture, where we set the derivative of this cost function equal to zero, and then we solve for the change in configuration at that point. And so if we work through that process, it's the result of it is shown then in the second half of this slide, right? So we set the derivative to zero, we work through and solve for the change in configuration, and what we arrive at is a change of configuration which is expressed in terms of this Jacobian pseudo-inverse portion here. And so that then is how the derivation for this process works, and it's what sort of shows that this Jacobian pseudo-inverse is also minimizing the squared error. So it also serves as an error minimization technique within inverse kinematics. The pseudo-inverse has a number of other uses. So sort of as a slight tangent, I just want to mention some useful properties of the pseudo-inverse, which allow it to be used to other areas within robotics and more broadly. In particular, to the problem of trying to fit polynomial equations to observed data. So the pseudo-inverse of a matrix, it turns out, is actually an approximate solution to a linear system of equations. And so linear systems of equations are used very broadly within engineering and across disciplines. So being able to approximate solutions to these linear systems has a very, very broad applicability. And so in particular, the pseudo-inverse of a matrix is this sort of best fit solution to what's called an overdetermined system of equations, where we have more equations than there are unknowns. And so as a result of that, the pseudo-inverse can then be used as an approach to fitting a polynomial equation or a system of equations to some observed data. So one example of this, which is nice to kind of play around with, comes from one of Professor Jenkins's former students. So this demo here, you can go online and actually view it. It's really neat. So it allows you to essentially add observed data points to the environment, and then fit a polynomial equation of varying degree to the observed data. And in particular, it's fitting this equation based on the least squares best fit approximation, which can be solved using the pseudo-inverse, as we're talking about. And so we discussed the pseudo-inverse during lecture 6 in our linear algebra refresher, but I wanted to include this slide in our lecture today just to refresh all of our memory on how it is we can compute the pseudo-inverse, because of course the particular because based on the size of the matrix, the particular pseudo-inverse that we are able to compute will vary. So there's a left pseudo-inverse and a right pseudo-inverse. So you compute the left pseudo-inverse when the dimension of your matrix A is such that n is greater than m, so when there are more rows than columns. And conversely, you would compute the right pseudo-inverse for the case when n is less than m, so that is when there are fewer rows than there are columns. So one additional topic I want to mention on this within this realm of error minimization or optimization for inverse kinematics are a number of considerations that we want to think about when we try and think about where else within robotics we can apply this idea of error minimization, and even within inverse kinematics specifically, some important considerations for thinking about how optimization can be used and what might be limiting it. So the first bullet point here is really an important one, which is that we haven't considered adding constraints within our inverse kinematics. So currently, all of our discussion on inverse kinematics has assumed that we simply want to find the joint configurations that will satisfy some desired end effector pose. But this ignores notions of joint limits, or if we have multiple end effectors on the robot which are going to share joints, so share degrees of freedom, or if we have preferred poses, or if there's collisions in the environment that we want to avoid. All of these concepts can be thought of as constraints that we would need to incorporate within our optimization routines, which up to this point we haven't considered. And so that's an important point to emphasize, is that there are extensions to these optimization-based approaches within inverse kinematics that can allow for these constraints to be added, and they're very, very crucial when you start implementing inverse kinematics on physical robot systems. Another important one is then to consider is the variance of gradient descent. So we've discussed what would be sometimes called vanilla gradient descent, but there's also variations, for example, stochastic gradient descent, where you would randomly essentially optimize one dimension of your configuration space at a time, as opposed to moving along a gradient step that's along all the dimensions of your configuration space. And in addition, there's a number of other important considerations that we might want to incorporate within optimization. So one of them might be understanding how our solutions based on this optimization are going to affect the manipulability of our robotic end effector. And so trying to understand the Jacobian and relate its configuration velocity to the actual behavior of the end effector is another important thing that we should think about when we try and make these techniques useful within robotics. These considerations also hint at a question that maybe there is actually a simpler approach to inverse kinematics that would alleviate some of these concerns. And so one that I want to briefly mention is what's referred to as cyclic coordinate descent, which is another variation of inverse kinematics, which has a very nice and elegant kind of conceptual approach to solving the inverse kinematics problem. And so the core idea behind cyclic coordinate descent is you're going to rotate one particular joint at a time such that the end effector lies within a plane that contains both the target pose of the end effector and the joint origin of the current joint that's being rotated. And so this process then will iteratively kind of move through the different joints on the robot, performing these rotations as an approach to move the pose of the end effector towards the target. So in this particular case, what would happen is if we're rotating on this, what's highlighted as this current joint, we would first apply a torque to this joint such that the current position of the end effector will lie on this plane that connects the target pose with the current joint's origin. And so then to illustrate where this fits in within this within the sort of iterative process of cyclic coordinate descent is illustrated on this figure. So we have some initial configuration of our robot with a desired pose of our end effector, and so you're going to iterate through each of the joints. So you might start with the farthest joint first, and so you're going to rotate that joint such that the pose of the end effector lies in this plane with the origin of the joint and the target end effector. So you can see that now the pose of the end effector lies on that same line. You'll then move to the next joint down the kinematic chain and again perform a rotation that will align the pose of the end effector to be coplanar with the target and the current joint axis. And then again, you'll move down to the final degree of freedom joint. Once again, perform a rotation that aligns the target end effector with, or excuse me, the end effector position with the target and the current joint origin. And then you'll repeat this process, and you're going to eventually converge on some final solution, which should be, or which should ideally be, positioning the end effector's pose to overlap with the target pose. So an external resource on cyclic coordinate descent, which has a nice demonstration and visualization of this, is linked on this particular slide here. But I just want to point out then a few pros and cons of cyclic coordinate descent in comparison to the Jacobian-based methods, which we've focused on in this lecture. So the first thing is that cyclic coordinate descent is very fast to compute, which is a really, really desirable property when you're trying to operate in real time for your robot. One downside is that the smoothness of the trajectory over time is not considered within cyclic coordinate descent. So in contrast to that, the Jacobian-based methods, which we focused on in this lecture and which we'll focus on for our assignment 5, these have the benefit of being a general transform of velocities. So they'll work across robots where you don't need to consider like the high-level approach can translate across robots. The downside with Jacobian-based methods in comparison to cyclic coordinate descent is that they tend to be slower, and typically you'll have numerical issues, especially when you're implementing the pseudo-inverse method, which is going to require an inverse matrix calculation. In addition, one other downside with the Jacobian methods is that they will always find a local minimum, and as opposed to necessarily a global minimum. And so with that brings us to the end of our lecture 12 here. So our second lecture on inverse kinematics. Next lecture, we're going to be talking about motion planning, and the sort of next topic within the class is going to be focusing on motion planning and extensions to what we looked at earlier in the semester. And so with that, thank you for watching, and I look forward to seeing you this week during interactive sessions, and especially at our robot showcase on Wednesday.